A storm event pipeline running smoothly for 3 weeks starts producing incomplete responses. Queries that previously returned detailed multi-event analysis now return summaries covering only one or two events. Nothing changed in the model, nothing changed in the retrieval layer, nothing changed in the data. What changed was the conversation history. The application was accumulating prior turns in the context window on every call. By week 3, the system prompts plus conversational history was consuming 3,200 tokens of a 4,096 token context window before a single retrieved document arrived. The retrieval layer was returning 5 relevant storm event chunks. The model was seeing 1. The budget ran out before the evidence did. This is Tokens, Context, and Why Budgets Matter, Models, Part 12. The context window is not infinite. How you fill it determines everything the model can see when it answers. Section 1. What the context window actually is. The context window is the total amount of text a model can process in a single inference call. Everything the model sees at inference time, the system prompt, the retrieved documents, the conversation history, and the user query must fit within the limit simultaneously. The model has no memory of previous calls. It has no access to information outside the current context window. Every inference call starts fresh with only what the context window contains. Context window size is measured in tokens. A 4,096 token context window holds roughly 3,000 words of English text. A 128,000 token context window holds roughly 96,000 words. Larger context windows give the model more work to work with, but do not eliminate the budget management problem. They change the scale of it. The critical property of the context window is that the model attends to all of it simultaneously when generating each token. A document at the beginning of the context window is as accessible as a document at the end, with one important caveat. Research across multiple model families has consistently shown that models attend more reliably to information at the beginning and end of the context window than in the information in the middle. For a pipeline that retrieves 5 documents and places them sequentially in the context window, the document in the middle positions are statistically less likely to influence the response than the ones at the edges. This is called the lost in the middle problem, and it affects retrieval quality independently of how good your embeddings are. Section 2. The 4 budget consumers. Every token in the context window belongs to one of 4 categories. Understanding what each category costs and what it contributes is the foundation of deliberate budget management. First, the system prompt. This is the only category that has a fixed cost. It pays the same token cost on every inference call regardless of what the user asks. A system prompt that runs 800 tokens costs 800 tokens on a query about a single tornado and 800 tokens on a query about synthesizing 15 storm events. Designing the system prompt to be as concise as possible while retaining its behavioral specification is not cosmetic economy. It is the budget allocation discipline. Second, retrieve context. This is the most variable in cost. The RAG pipeline retrieves document chunks from the vector store and places them in the context window between the system prompt and the user query. Each chunk costs tokens. A retrieval configuration that returns 5 chunks at 400 tokens each costs 2,000 tokens before the user query arrives. A configuration that returns 10 chunks at the same size costs 4,000 tokens. The number of chunks retrieved, the size of each chunk, and the order they are placed in the context window are all budget decisions with direct consequences for response quality. Third, conversation history. This is the one most commonly responsible for the failure pattern in the opening scenario. Multi-turn applications that retain prior conversation turns in the context window accumulate token costs with every exchange. A 10-turn conversation where each turn averages 200 tokens adds 2,000 tokens to the history to every subsequent inference call. Without a strategy for managing history length, context window exhaustion is a when problem, not an if problem. Fourth, the user query. The query is typically small, rarely more than 100 tokens for a focused question. The response budget needs to be explicitly reserved. A model given no guidance on response length will generate until it reaches a natural stopping point, which may consume more tokens than the budget can accommodate after the first 3 categories have taken their share. Section 3. Budget allocation for the NOAA pipeline. The NOAA pipeline runs against a model with a 4,096 token context window at the minimum viable hardware tier. That budget is allocated as follows across the 4 consumers. The system prompt designed in Part 11 targets 400 to 600 tokens. Call it 500 as the budget figure. That leaves 3,596 tokens for everything else. Our response reservation should be explicit. A detailed storm event analysis response that covers multiple events with citations and a confidence assessment runs between 300 and 500 tokens. Reserve 400. That leaves 3,196 tokens for retrieved context and conversation history combined. If the application maintains no conversation history, the full 3,196 tokens is available for retrieved context. At 400 tokens per chunk, that accommodates 8 chunks comfortably. 8 storm event chunks covering a single query is generous retrieval coverage for most questions. If the application maintains a conversation, the history budget needs an explicit ceiling. A 2-turn history at 200 tokens per turn costs 400 tokens, leaving 2,796 for retrieved context. A 2-turn history means the pipeline reads the 2 most recent exchanges between the user and the model. 1 user query plus 1 model response counts as 1 turn and discards everything older. It is a sliding window that moves forward with each new exchange, keeping recent context available in the model while preventing history from accumulating without bound. A 5-turn window costs 1,000 tokens, leaving 2,196. Setting an explicit maximum history length and truncating or summarizing older turns when the limit is reached is not optional for a production pipeline that runs multi-turn sessions. Section 4. Chunking Strategy Revisited. Part 6 made chunking decisions based on document structure. Part 3 specified the minimum viable hardware. Token budget management adds a second constraint to these decisions. A chunk size of 400 tokens was specified in Part 6 based on the coherence of NOAA storm event narratives. That chunk size also fits the budget allocation mentioned above, with room for meaningful retrieval coverage. The 2 constraints, document coherence and budget fit, happen to align for the NOAA dataset. They will not always align for every dataset. When they conflict, the budget constraint wins. A chunk that is too large to allow sufficient retrieval coverage in the available context window is worse than a slightly less coherent chunk that fits. Retrieval coverage means the number of distinct chunks the pipeline can surface into the context window for a single query. If a chunk is 800 tokens and the available retrieval budget is 2,400 tokens, the model sees 3 chunks. If the same content is chunked at 400 tokens, the model sees 6 chunks covering twice the ground. A response synthesized from 6 relevant chunks is more complete than one synthesized from 3, even if each of the 3 was slightly more internally coherent. Coverage wins over coherence when the budget forces a choice. The 50-token overlap specified in Part 6 costs tokens at the boundary of every chunk. For 8 chunks with 50-token overlaps, the overlap cost is 400 tokens spread across the retrieved context. That cost is worth paying for the context preservation it provides at the chunk boundaries, but it needs to be accounted for in the budget rather than discovered as an unexpected drain of available context. Section 5. Hardware equals larger context windows. The minimum viable hardware tier uses models with 4,096 to 8,192 token context windows. Mid-range hardware accommodates models with context windows ranging from 32,000 to 128,000 tokens. The budget management discipline described above applies at every context window size. The numbers change, the principles do not. A 128,000 token context window does not eliminate the lost in the middle problem. It expands the middle. A retrieval pipeline that surfaces 50 documents into a large context window faces a more severe version of the positional attention problem than one surfacing A documents into a small window. Larger context windows enable more ambitious retrieval strategies but require more deliberate management of the document ordering and relevance filtering to ensure the model attends to what matters. For the NOAA pipeline, the minimum viable context window is sufficient for the query types this dataset supports. The upgrade path to larger context windows is available when the use case requires it and the hardware supports it. The budget discipline learned at 4,096 tokens transfers directly. Section 6. Tracking token consumption in production. Every inference framework that serves language models exposes the token consumption metrics. OLLAMA, VLLM, and the serving infrastructure covered in Part 17 all report prompt tokens, completion tokens, and the total tokens per inference call. Logging these metrics from day one is not optional instrumentation. It is the data that tells you when conversation history is accumulating towards context exhaustion, whether your chunk size, retrieval count are consuming the budget as planned, and whether the response length is staying within the reserved allocation. At this point in the article, there is a Claude Code prompt that you can see in the Substack firsthand. What you're asking Claude Code to build is a token tracking and budget enforcement layer that sits between your application and the inference server, logging consumption, enforcing limits, and managing conversation history automatically. The daily summary is what tells you whether your budget allocations from this article are holding in production or drifting over time. What success looks like is every inference call produces a log entry with token counts. The budget warning fires on calls where prompt tokens exceed the threshold. The history manager truncates correctly when the rolling window limit is reached. The daily summary produces numbers that match manual inspection of the log database. Next, with the system prompt designed and the token budget understood, the deployment has everything it needs to add retrieval. The next article covers what RAG actually is, why it is the right first move before fine-tuning, and how the retrieval layer connects the vector store to the model at inference time.